Welcome back. And in our last mini lecture, we talked about systems thinking and how a combination of systems thinking and computer programming is incredibly powerful for making sense of complex ecological systems, real world systems, and for, ultimately making management recommendations and conservation recommendations. This is, after all, an applied population ecology class. So that's where we started. But interestingly, this is a population ecology class, and we have not yet really talked about population ecology. So let's move to the next lecture, where it's called Introduction to Population Ecology. So on our website, let's move to that lecture and start talking about what population ecology is. And I'd like to start off by just pointing out the most fundamental concept of population ecology, and that is exponential growth. And so what we can see here, looking at the human population over the last couple of centuries, it's not as linear as that moose model we made. It's not like a straight line. It's a curvy line, and the curvy line has a specific form to it, and that it kind of accelerates over time. You have this really low rate of growth back in the 1800s, and then as soon as the late 1800s and 1900s rolls around, you start to see the slope of this line start to increase. You have this accelerating relationship where as the population itself gets bigger, the rate of the growth of the population gets bigger. And so you have what's called a snowball effect or a vicious circle, whatever you want to call it. It's exponential growth, and it is the most fundamental concept of population ecology, because living organisms have this power to grow exponentially. It's an incredible power, and it's a power that, if left unchecked, any species on Earth could potentially basically overtake not only the Earth but the universe if left to grow unchecked, because the power of this growth is incredible. Given enough time and enough generations, essentially any species would be able to achieve unrealistic, crazy high numbers because of exponential growth. So we'll come back to this many times, but this is where I wanted to start in this lecture on basic population ecology. But let's first take a step back and talk about some of the questions that motivate population ecologists and have motivated population ecologists from the very beginning of this field. And so we can divide these questions into some ecological or basic biological questions about how species work, and we can talk a little bit more about how some biologists are more trying to apply these concepts to conservation and management, and this is an applied ecology or applied population ecology class, so of course that's where we're going to ultimately go ourselves. And so some of the ecological questions that motivate population ecologists of the past and of the present is questions like, why are some species more abundant than others? What causes population densities to vary not only across space but across time? How can we better understand population dynamics? What causes populations to become extirpated or extinct? What causes entire species to become extinct? How do populations become recolonized? What processes regulate population growth? We talked about exponential growth and how it's basically has this capability. Living organisms and populations have the capability of basically taking over the planet given enough generations. What processes prevent that from happening? How do populations become regulated, essentially? We'll talk more about that in a couple lectures down the road. What prevents predator-prey relationships from collapsing? And what prevents competition relationships from collapsing? If you're in an antagonistic relationship with another species, whether it's you're competing with them for resources or one eats the other, why can these populations both be sustained? Why doesn't the predator just outconsume the prey and then the predator's outlook doesn't look good if there's no prey? So how do these systems maintain themselves? How are these ecological relationships sustainable? And what factors allow metapopulations to be stable? So metapopulations are just populations of populations. Essentially, you can think of lots of patches on the landscape. Some patches are occupied with a focal species, and some patches are not. And these patches kind of wink on and off. And given these metapopulations are dynamic, what factors allow metapopulations to be stable and self-sustaining at the higher metapopulation level? All right, from a management perspective, some of the questions that motivate applied population ecologists are things like just assessing the conservation status of a focal species. If you're working with an at-risk or rare species, we just want to know, is the species declining? Is there a risk that the species may go extinct in the near future? What's the conservation status? And we might be interested in knowing how human development, how anthropogenic processes are affecting these species of concern. And if possible, if there's anything we could do to potentially reverse the negative trends that we're seeing, if we can understand the processes driving a decline, we might be able to improve the conservation outlook for that species. For harvested or game species, what's the maximum sustainable yield? How many individuals can be removed from a population in a given time period, and the population remains self-sustaining? How can pest species be effectively controlled? Population ecologists are investigating outbreaks of insect pests in agricultural fields, and how that outbreak process works, and potentially how to control those outbreaks. What specific land areas can be protected to preserve at-risk or species of conservation concern? How do we manage metapopulations where the habitat may exist in these patches of habitat that are separated by non-habitat? Which patches should be protected? How can we improve certain patches to improve the outlook for the entire metapopulation? And what are the likely population level effects of alternative management and conservation actions in general? And in our final projects in this class, we're going to be building in groups population viability analyses, which are just population models that are built and designed to answer this question: which conservation actions, what management actions would be most beneficial for that species given what we know about the species. So we'll be doing a lot more with this, and all of us will be addressing this question in our final projects. All right, this is a population ecology class, so we need to be able to define what a population is. And it's not as simple as it might sound, because sometimes it sounds really simple. A population is just a group of individuals, but it's not always that easy to define which individuals belong to a population and which belong to a different population, or is this a metapopulation? So we need to define population, and of course, this is likely to appear on an exam, so be very conscientious about learning and understanding this definition. I like to use the definition from Krebs, 1972, which is: a population is defined as a group of organisms of the same species, obviously, occupying a particular space at a particular time with the potential to breed with one another. All right, so if individuals of the same species are in a close enough proximity, and of course they have to be existing at the same time, otherwise they cannot breed with one another. If they are, then they should be considered to be in the same population. Individuals of the same species, close enough proximity that they could potentially, not that they will, or not that they, have a high likelihood to, but they could potentially breed with one another. So that is the definition I like to use. It's fairly straightforward. There are other definitions out there, but for this class, let's use the Krebs 1972 definition. And please make sure that makes sense. If it doesn't make sense, just let me know. Now, it sounds fairly straightforward, but again, defining in a real world case. So you can think of a species you're interested in, and then start thinking about how you would define who's in the same population and which individuals might be considered to be in a separate population. It starts to get a little muddy. Spatial boundaries defining populations are not always easily defined. Sometimes we have species that exist kind of in a continuous space, extending for a very long way. So we might imagine, let's see, a large forest that's inhabited by a squirrel species continuously, and the forest is so large that squirrels in one end of the forest would not really be able to potentially breed with individuals hundreds of kilometers away, for instance. So are they all in the same population? And if they're not, where would you draw the boundaries? It's not always very clear. In some cases, it is clear. In some cases, like, for instance, I've worked with semi-aquatic freshwater turtles in the past that are occupying discrete ponds on the landscape. Each pond can be considered its own population fairly easily. Individuals in the same pond can potentially breed with one another, and they don't switch ponds very often. So it's nice. These ponds have nice discrete spatial boundaries. It's very easy to define, but it's not always easy to define. All right. So that's, and just know, and we'll talk about this more in lab on Friday, but population size, which we in Insight Maker represent as a stock, one of those boxes in the workspace in Insight Maker that stores things, in this case a population. Mathematically, we represent the population size as big N. So just know that this symbol, you'll see it a lot. This big N, that represents the number of individuals in the population at a given point in time. And that's the most basic measurement that population ecologists will make. So that we'll go over the mathematics in lab, so we're not going to do that now. But I do want to talk a little bit about exponential growth, which, did I mention, is the most fundamental principle of conservation biology. So it's really important to start wrapping our heads around this incredible power that living things have to grow, not linearly, but in a runaway exponential fashion. Let's consider this example of the giant puffball. Giant puffballs produce, and this is an extreme example, but it's making a point here. The giant puffballs produce 7 trillion offspring, that's 12 zeros, in one reproductive event. If all those individuals reached adulthood, the descendants from just 2 parent puffballs would weigh more than the entire planet in just 2 generations. All right? And the reason, of course, is that populations grow exponentially, and that is a tremendous power. And we'll talk more about that in the next lecture, where we talk about Thomas Malthus and who was applying this concept to the human population growth, and recognizing that we can't grow exponentially forever and not encounter serious issues such as famine. We may outstrip our own resources. So we'll talk about that next time. Let's, before we move on to building exponential growth model in Insight Maker, this is kind of an aside, but I just want to talk about mathematics and population ecology, because mathematics has been a part of population ecology from the very beginning. It's not something that ecologists often really like to do, but it's something that is incredibly powerful. And so we will be doing mathematics in this class because population ecology is a mathematical discipline. And I want to just make the point of this uneasy relationship that ecologists have with mathematics. And this goes back to the very beginning of ecology. Now, the first quote I like to share here is from Charles Darwin, who said, "Mathematics seems to endow one with a new sense." And I like that quote because mathematics really is kind of a different language that allows us to look at natural phenomenon in a more precise manner. Mathematics is a language of logic and precision, and so it really does allow us to see things we might not otherwise have seen. So in that sense, it is a sense. And Charles Elton, who many consider to be the father of ecology, has this wonderful quote here where he says, like most mathematicians, and he's referring to a man named Alfred Lotka, who you might have heard his name in the Lotka-Volterra predation and competition relationships, which we'll talk about more later. So Lotka is one of the founding fathers of quantitative population ecology. And so anyway, Charles Elton is talking about Lotka here and saying, like most mathematicians, Lotka, takes the hopeful biologist to the edge of the pond, points out that a good swim will help his work, and then pushes him in and leaves him to drown. So clearly a little bit uneasy with the idea that mathematicians have a lot to offer to the field, kind of reluctantly saying that maybe there's value here, but but the ecologist doesn't really know what to do with it. But here's another quote that comes again from Charles Elton, referring to Lotka's work, and he says, "The importance of the method is this: if we know certain variables, mostly desired by ecologists and in some cases already determined by them, we can predict certain results which would not normally be predictable or even expected by ecologists. The stage of verification of these mathematical predictions has hardly begun, but their importance cannot be underestimated, and we look forward to seeing the further volumes of Lotka's studies." And so that's a little bit of a mouthful there, but what is Charles Elton really talking about? And we talked about this last time too, when we were talking about systems thinking and what happens when we put simple relationships together, a system with simple relationships defining interactions, like the lynx and hare example, and we see that interesting, unexpected things emerge. Those things are called emergent properties, and we can learn about those things through modeling and through mathematics, and that is why Charles Elton is so excited in this in this quote to be delving into the models that Lotka has introduced to ecology. So the moral of the story here is not to be afraid of mathematics. Mathematics is a part of population ecology. It endows us with a new sense, like Charles Darwin said, and it allows us to see things like emergent properties of our systems that we wouldn't otherwise be able to see. And so it is, it's essential, and hopefully you'll see it's not really that difficult. The models that we're talking about are not really crazy difficult mathematics, all right? But it's still incredibly useful. So bear with us and don't be afraid of the mathematics. And I will say the textbook for this class, the Gatelli book, scares some people away, because if you turn to any page of the book, I'm just turning to a random page, you'll see, what do you see? Mathematical equations. Don't be afraid of those equations. We're going to talk about we're going to talk through these equations in plain English. And we'll talk through the mathematics, and we'll try to go slow enough. And all of these equations, basically, in the Gatelli book, they're not that complicated. Don't be afraid of them. Maybe the first time you read the chapter, it's not going to make total sense, and some of the equations will kind of go over your head. That's okay. We will talk through it in lecture. We'll talk through it in lab, and you can come back to the Gatelli book, and hopefully by the end, once you had a chance to digest the lecture and the lab materials, it'll all make sense. So don't be afraid of the mathematics. All right. And before we end this lecture, I just want to point out that population ecology is not, it's not a static field. It is constantly growing. We're learning more and more about how populations work and how to translate what we know about populations into conservation and management. It's a very active field of research, and it's continuing to be developed. And many of the questions that ecologists ask, some of the biggest questions asked by ecologists, have a lot to do with population ecology, as well as other parts of ecology. I just want to point out that there was a paper by Sutherland et al. In 2012. You can link to it here if you'd like to read the paper. It's optional. And it just goes through some of the most pressing questions in ecology. And I'm not going to go through all these questions, but I encourage you to read through the paper and even look through the questions listed on the website. It's optional, but and you probably will understand these questions better by the end of the class. Some of them might not make complete sense now, but things like, what governs the range margins of different species? This happens to be the common juniper, but why does it occur up here and not down here? So these kind of questions, you can ask questions about prey-predator interactions and the importance of direct predation versus indirect consequences of having a predator in the landscape, such as the prey avoiding open areas where they can be seen by predators and that kind of thing. So that is induced behavioral change versus direct predation. We can look at how important are rare species in the functioning of ecological communities. So there's lots and lots of interesting questions that are really limited only by our imaginations. All right. So in our last Insight Maker demo, we built a very basic model, but that model was pretty unrealistic. And I think we've already gone through some of the reasons why that model was unrealistic. And when we ran the model, it just showed this linear growth that looked very different from this type of growth. So what we're going to do in our next Insight Maker demo is to build a model that is more realistic, that looks like this, and it grows exponentially. And so let's talk a little bit about that process of exponential growth and what it is. And I'm going to talk about it in the context of systems thinking, and I'm going to talk about it using the word feedback. Feedbacks are what makes systems really interesting to work with, and typically feedbacks are what lead to things like emergent properties that we might not expect. What is a feedback? A feedback is when the amount in a stock influences the rate of change of that stock. In that moose model we made, the total number of births was constant every year. So no matter what the level of number of moose in the population, the birth rate was the same. You always get one or two individuals, whatever we specify, entering the population every year. The same number entering every year, regardless of the size of the moose population. There's no feedback there because the rate of change is not dependent on the amount in the stock. That is the number of moose in the population in that case. And a feedback is when the rate of change of the stock actually depends on the amount in the stock. So let's think about this figure here. We have a population, and we're thinking about the rate of change just in terms of the number of births that are entering the population. All right. So the more individuals in the population, the more births. And let's think through why that might be. It should be pretty obvious that the more individuals in the population, and if each individual in the population gives birth to, say, on average 1.5 new individuals, then if you have a population of 10 individuals, you should have 15 births, right? But if you have a population of 100 individuals, you should have 150 births. So because each individual, on average, 1.5 offspring. So the more individuals in the population, the more births you'd expect, right? So there's a positive relationship between population and births. And of course, the more births there are, the more new individuals enter the population, and the bigger the population gets. The bigger the population gets, the more births you're going to get, and so on and so forth. And this is what exponential growth is all about. It's a positive feedback. Positive feedbacks are also known as vicious circles, can be called the snowball effect. In any case, it is runaway growth. That's what it is. There's nothing stopping it. You have a positive relationship. The bigger the population is, the more the higher the growth rate, and the higher the growth rate, the bigger the population is, and it just goes on, and ultimately takes over the universe, right? So that's a positive feedback. And exponential growth is what we see when a positive feedback is in effect. Populations are capable of having this positive exponential feedback because, clearly, as we just saw, the bigger the population is, the bigger the growth. That is, the more individuals are expected to enter the population, the bigger the population is. That's just how life works. Okay, that's a positive feedback. What's a negative feedback? There's both types of feedbacks are in operation in most systems, and if all systems only had positive feedbacks, there really wouldn't be the chance of life existing, really, because what we need is some kind of stability. We need to be able to stabilize systems so that they can sustain indefinitely. Think about our own bodies. Our bodies maintain temperature at around some really relatively small window. Fluid balance. You can think about pH, sodium, potassium, calcium levels, all within a very narrow range. Blood sugar levels, all within a very narrow range. This is called homeostasis. This is the process that all living organisms have to maintain life itself. We have to maintain kind of regulated levels of these really important things like water and hydrogen ions and all these things. So that's homeostasis, and that really, homeostasis can't happen with something like this. This is a runaway growth. Negative feedback is more regulatory. Negative feedback, the bigger the stock is, maybe the smaller the change is. So if the population gets too big, the growth rate goes down. If the population goes too small, the growth rate goes up, and the population maintains itself at a given level, which we often call carrying capacity in the case of population ecology. And that is a negative feedback loop. So anytime you think about negative feedbacks, we can think of homeostasis and regulation at a sustainability over time. And so the reason for that is, again, if the population gets too big, the birth rate goes down, and the population kind of self-regulates. If the population gets too small, the birth rate might go up, and the population goes back up to this stable, sustainable level. And so that's the difference between positive and negative feedbacks. Both are incredibly important and to know about and to be able to model. And we're going to be working with both types of feedbacks in the near future. But the first thing to do is to explore the positive feedback and build a model that includes exponential growth. So that's what we're going to do in our next video.